Okay, so in this example, we are going to show that there exist domains where irreducible elements are not necessarily prime. And so here is a subset of the ring of polynomials with integer coefficients. And this is these are polynomials without a linear term. You should be able to, at this point, you should be able to convince yourself using the subring test, and that's what it means when I say convince yourself, that R is a domain. It's a straightforward application of the subring test, and if you ever find yourself asking the question, do I have to do it? The answer is yes, because you're asking the question. And so take a moment, show this is in fact a subring of Z adjoint X. And since it's a subring of a domain, it is in fact also a domain because it's a non-zero subring of a domain. Great. So let's see. Um, this guy is a domain, and I claim here that the element x squared is irreducible. In fact, suppose that you could write x squared as a product of polynomials. Then we're going to apply the degree function. So we can take the degree of x squared, and we can take the degree of f times g. I'm going to drop the of x notation. The degree of x squared is certainly 2, and the degree is also additive. So it takes multiplication to addition. So the degree of f and the degree of g, whatever they are, they have to add to 2. Well, there's only a handful of choices up to order. There's 0 and 2, and there's 1 and 1. But our ring here doesn't have any polynomials of degree 1. We explicitly have excluded polynomials without a linear term. So this cannot happen. In particular, the degree of f must be 0, and the degree of g must be 2. So this implies that f is a constant, and g looks like some a0 plus a2x squared. Let's write this constant as c. So we have that x squared is equal to c, which is f, times a0 plus a2x squared. Or equivalently, x squared is c times a0 plus c times a2x squared. In particular, well, c can't be 0 because then the product would be 0. So c is not 0. Let's just put that in there. So this tells us that a0 has to be 0 to make the sides match up. And c times a2 needs to be 1. And so we have two possible factorings of x squared. We either have x squared is negative 1 times negative x squared, or 1 times x squared. And those are the only possible factorings in this ring R. And in both cases, these are units. So if we have a factoring, well, these are the only two possible cases, then one of the terms has to be a unit. Okay, it is. So we conclude here that x squared is irreducible. Only the silly factorizations are here. All right, now let's show that it's not prime. Let's make an observation. And the observation here is that x squared does not divide x cubed in R. It certainly divides x cubed in all of z adjoint x, but we don't have all of z adjoint x. We're not allowed linear terms. And the reason why this doesn't work is because if it were true, then, well, x cubed is x squared times some polynomial. And then we apply the degree. So the degree of x cubed is the degree of x squared plus the degree of p adjoint of p. I'm going to drop the of x notation. And that's 3 is 2 plus the degree of p. And this would tell you that the degree of p is 1. In particular, p is linear. But this is a contradiction because R doesn't have any polynomials with linear terms. We have no degree 1 polynomials. So x squared cannot divide x cubed. And yet, x squared does divide x cubed times x cubed. And the reason why it divides x cubed times x cubed is, well, x cubed times x cubed is x to the 6, and x to the 6 is x squared times x to the 4th. And both of these polynomials are in R. So x squared and x to the 4th are in R, certainly. So x squared divides this product. Well, not but there, I'll put the but here. X squared doesn't divide either of the terms in the product. They're both the same terms, but I'm going to write it twice. So this means x squared is not prime. It's not a prime element. All right, so here's an example of a domain where there's an irreducible element which is not prime.